Hello again. We're going to talk about section 15.3, and I want to introduce this idea of tangents and circumscribed angles. Let's start with tangents. All right, a tangent to a circle, if we read it here, is a line that is in the same plane. And all that means is that if a circle is lying on the table, the line is also lying on the table. We can't have a circle and then a line going through it like my pen here. Okay, we can't have that. All right, and so it intersects the circle, and this is the key to tangent, exactly 1 point, okay? It intersects the circle in exactly 1 point. That's key, okay? Over here in our diagram, P is that exactly 1 point, okay? P is that exactly 1 point where we intersect the circle, okay? Let me go back. All right, and so let me get my color here for you. All right, so P intersects the circle in exactly 1 point. Now, the point where the tangent and the circle intersect is called the point of tangency. Okay, so let me just make this line L. So L is the tangent line, P is the point of tangency. Now, it's not written here on this slide, but something you want to be aware of is that the radius and when the center connects with the point of tangency, you would always create a radius, because isn't a radius any line that goes from the center to the side of the circle? Okay, so the center to the point of tangency always forms a right angle, always, always, and forever. And so that is what is most significant about a tangent intersecting a circle, is that you automatically have a right angle with the radius. Now, look at this case here. Was the radius drawn in? No, but we know every circle has a radius, okay? And so we've now discovered that L is the tangent line, P is the point of tangency, and this segment CP is a radius. The radius and the tangent always form a right angle. All right, so next we want to talk about what is this circumscribed angle. Now, if you remember, we've already discussed what an inscribed angle is. I'm just going to use the same diagram. Let me get us a different color here. An inscribed, remember an inscribed angle, the vertex is on the circle. Well, notice the two diagrams below. Here we have the vertex of the angle is outside the circle. The vertex of the angle is outside the circle. And that's because for circumscribed angles, they are formed with two tangents, and those two tangents intersect outside the circle. So if you look here, a circumscribed angle of a circle and its associated central angle are supplementary. Okay, so we remember supplementary equals 180 degrees. And so that means angle H and angle F are supplements of one another. Now, what does it mean, associated central angle? Okay, look at this diagram here to the right. Do you see that angle GFJ and this angle GHJ? Don't they intersect the circle at the exact same endpoints? Get my pen to work correctly here. Okay, so they intersect the circle at exactly the same endpoints. And that's what it means, associated central angle. So when you take the circumscribed angle, again, made by two tangents, okay, GH is a tangent Y. It intersects the circle at exactly 1 point. JH, that segment is a tangent. It intersects the circle at exactly 1 point. Therefore, that angle H and angle F are supplementary. Okay. Now let's think about what else we know. Remember, we also said a tangent, GH is a tangent, FG is a radius. That means we automatically know this is a right angle. This is also a right angle. Okay. Now you know I love connections. So look at this. Do you see that? If I draw this line, don't I have two triangles? They're right triangles. And we know so much about triangles. So remember, it always comes back to triangles. Let me clear all these drawings a second so you guys can see this. Okay, now Let's talk about the two tangent theorem. Here we have tangent AX. How do we know? Because it intersects the circle in exactly 1 point, okay? Here we have B intersects the circle in exactly 1 point. Okay, so those are tangents. AX, XB is a tangent, therefore two tangents intersecting at the same point X. This angle AXB is a circumscribed angle. A circumscribed angle created by two tangents. Okay, so now that we have that, if the two segments from a same exterior point are tangent to the circle, what else we learned? This segment is congruent to this segment. Now, are those chords? No. A chord is a segment inside a circle. And notice here we made the distinction, exterior of a circle, interior of a circle. Okay, and so interior of a circle would be where we would find a chord. Exterior of the circle, we just find a segment. And when that segment intersects a circle in exactly one place, we call that segment a tangent. So if two tangents intersect outside the circle at the same point, in this case, that would be X, then we know this segment AX, this segment BX are congruent. All right, so then let's use that to come over here and solve and answer this question. What all do we know about the diagram if we know points G and J are points of tangency? Well, I've already given it away a little bit. Let's see if you could pick it up. G and J are points of tangency. FG, FJ are radii. How do we know they're radii? Any segment from the center to the side of a circle is always a radius. So that means we know this is a right angle. That's one thing we know. This is also a right angle, where the tangent meets the radius. Okay, two tangent theorem tells us that this segment GH is congruent to JH because they intersect at a common endpoint outside the circle. What else do we know? Don't we know that radii are equal? Therefore, FG and FJ are congruent segments because the radii of any circle, the radius within any circle, are always congruent. So these are all facts that we know simply by what has been covered already in Module 15. All right, you guys, I'll see you next time to cover circles within the coordinate plane.